Hello, everyone. Welcome back to the AAS YouTube channel. And today we're going to start something new. We're going to start a AAS Journal data series to talk about all things data in AAS Journal articles. And of course, with the advent of AI and machine learning and advanced statistics, this is a very hot topic, or subcomponent in astronomy these days. And so I thought it would be good if we had a series on this. And to help kick this off, I am super happy to have Mumdi Rahman with us today. And Mumdi is a scientific editor for the AAS journals, and he particularly works in the corridor of laboratory astrophysics, instrumentation, software, and data. So Mumdi, hi.
Thank you so much for having me.
Oh, well, thank you so much for agreeing to share your expertise on some of these topics with us. I'm very excited.
I think we're gonna have a lot of fun.
I think so too. I love your setup. You've got quite the mic boom and the soft fade in the background. You have an excellent setup.
Well, I'm particularly happy to show off the that's actually a print of the patent of the telescope from the U.S. Patent Office. So that's always fun to, perfect to set up a little bit about what we're going to be talking about somewhat.
Absolutely. That's very cool. So where are you located, Mumdi?
So I am based out of Toronto, Ontario, Canada.
Oh, okay. Okay. So we're going international.
So a little north of the border, but not too far north.
And how is, so it's July 14th on 2021. And how is summer in Canada these days?
Summer is, I mean, it's hot. It's, we've been getting sort of, we work in Celsius, so we've been getting like 30-degree days easily here. So it's, it's not all the winter igloo chill that everyone, south of the border seems to think Canada's associated with. It gets warm, but it also does get cold.
Very good. We are actually a little bit cooler today in Phoenix. So normally we would be up in the 40 Cs, 43 Cs.
Oh, wow.
But we got a desert thunderstorm this morning at about 5 a.m. So we had lightning and thunder and lots of rain. And so things are pretty cool, humid, a little more humid, but cooler in Phoenix today. So
do you guys get all the desert blooms that come out of the thunderstorm, like all the flowers that pop up? That's incredible. I would love to see that one day.
When the cactuses, after a desert rain, is when they decide to throw out their once-a-year flower, for example.
That would be, yeah, I would love to see that.
Wait, I should take a picture of one and post it.
Yeah.
Cool. Let me just ask, Mumdi, what do you like to do for research?
So I'm kind of all over the place. I really love dealing with large amounts of data, right? Like that's, and trying to figure out what the stories within it are. So a lot of my background has been in star formation and a lot of, galaxy evolution, understanding star formation through the scope of the Milky Way. But lately I've been dealing with big data in a large, scope of things. So my latest projects are on fast radio bursts and detecting them, trying to figure out and localize where they are. So a little all over the place.
Very cool. Very cool. And at some point in the future, we'll get you on and do a scientific editor chat.
That'll be a lot of fun.
Be good. So let's go ahead and get into it. And this is going to be the kickoff of the AAS Journal data series. And so I will do a screen share here. And here we go. And Mumdi, take us away.
Awesome. Well, today we're going to be talking about 10 things not to do in a plot. And this is such a critical thing for how we talk about science and how we present science and also how we figure out science, right? So much of the way that we're looking at new results or data as a whole is through the visual. And so getting that, getting comfortable with it and understanding what are the things that you may not realize that you're doing, but changing one little thing would dramatically improve how people look at your figure, how people understand the science behind it. That's what we're going to try to aim for today. And so we've got this as a top 10 list. Cool. And so we're going to go through, one by one. So Frank, why don't we go to the number 10? So the number 10, on the list of top 10 things not to do on a plot is make your plots inaccessible. So for the rest of the rules and the rest of the points that we're going to be showing here, there's probably reasons to break those rules, right? And rules are made to be broken. And you can think of great ways for, and great reasons and creative and innovative reasons to break these rules, but this is not one of them. You do not want to make your plots inaccessible. And what do I mean by that? Well, let me ask actually Frank, what would you, if you had to pick the most common visual processing challenge, physical challenge that people have, what do you think it is? It's
color.
So that is the most common answer, is color blindness. It's not actually the correct one. So color blindness affects about 5% of human beings. It actually ends up being a big concern, and it's certainly something that we want to take care of. But actually the answer is dyslexia. So much of, so it's about 20% of people are affected by dyslexia in some mild or serious, serious manner. And this significantly affects how people interpret visual information.
Okay.
And so needing to think about how to make plots accessible and figures accessible for that is actually one of the most critical things that we can do to help people understand it. And something that I'd like to bring up is something called the curb cut effect. So I'm sure, Frank, you guys have curb cuts over in Arizona. You're familiar with them?
No, but go ahead.
Okay, so curb cuts are, it's a fun little story where basically they are areas in the curb. So if you're on a road and you have an area in a curb where the sidewalk is supposed to end and you're supposed to go onto the road, there's a little cut usually made nowadays, usually made in the curbs to allow, for instance, originally for wheelchair accessibility.
Right.
So this obviously wasn't always the case, unfortunately, and many disability rights activists in the United States, primarily actually in Berkeley, got this passed as a part of the Americans for Disability Act. Right. But what they found as these things were being installed all across is by helping that one community with this challenge, it helped a wide variety, right? Mothers with strollers or people with strollers, anyone who has, physical mobility challenges of whatsoever. It was just end up having massive repercussions for a lot of people.
Children.
And so, exactly. Yeah, no, entirely. And so this is the way to think of accessibility. And especially when it comes to visualization, when we talk about the things that really are critical to helping somebody with a visual challenge, recognize your plot or understand your plot, these are things that are going to help everybody take a look at it and better understand it. So let's talk a little bit about what some of these look like. Can we go to the next one? Okay, so one of the big ones is spacing and the use of space. That's one of the most critical pieces to being able to have people associate visual elements together. And so, for instance, a lot of things that we think are aesthetics actually have a basis in the way our human brains understand the placement and the shapes of things. And so there's right ways of doing it and wrong ways of doing it. So one example here is this is a Goldilocks problem where, if you have too little space, then it looks crowded, and it's actually very difficult for somebody, especially with visual interpretive, challenges, to really distinguish it and understand what's going on within that. So that's the bottom one. The top one, if there's too much space, it's very difficult for them to actually associate together and do comparisons and recognize that they should be comparing them. So the middle one is the kind of thing that you want to aim for, right? Thinking about the white space and how it relates to how things are related on your plot.
The perfect porridge there for the Goldilocks.
Exactly. It's a classic Goldilocks problem. But let's go to the next slide. It's one of the other things is sort of mental encoding, right? One of the challenges that we don't think about when we're often making a plot is how much do I need to remember to interpret this plot? That is an inherent challenge, depending on how you visually understand something and how you would visually interpret something. So on the left-hand side is what would normally be a perfectly fine plot, right? It's just 3 bars, obviously you want axes and things like that on it, but 3 bars with a legend of what those are. Well, one easy way of changing it, making it more visually understandable, interpretable, is having the labels be directly associated with what they're representing. Right. This massively changes the amount of complexity and decreases the amount of complexity that you need to understand what's going on in this.
Absolutely. Yeah. Yeah. And we see a lot of examples of these in our scientific editor work.
Yes.
Where sort of people will use a default plot that automatically puts this kind of a legend off to the right.
Right.
Or it's just a lot cleaner to get rid of the legend and label what it is you're doing. Rather, there's just an extra step here. Oh, purple is quasars, which goes over here, whereas here it's boom, immediate.
Entirely, yeah. And it gets you right to the point. One of the things that you really want to do is, as much as possible, you want to make the operations of looking at a plot invisible, right? You don't want the person to have to think to understand it.
Right. No.
But speaking of color blindness, and that's the next slide, one of the things you do want to do is make sure that you choose and make color choices that are accessible and are sufficiently distinguishable. And there's a lot of tools on the internet. One of the ones I recommend that is free that I've shown here is Adobe Color, where you can actually put in colors and then ask, what are the visual challenges? In this case, it tells you, for instance, it shows you what the two, what the colors would look like with different types of color blindness, and it tells you which of the colors you need to separate more and what direction they should be separated more.
Oh, nice.
And so it's a fantastic, easy way, because you can then just grab those colors. All of them are provided in RGB, the standard, RR, GG, BB kind of format. And then you can put that into your Python or your R or IDL or MATLAB or whatever you'd like to use, and use those colors, and you have something that will work. And that is always something that you can set and forget at some level.
Right. And on occasion, people who are getting the referee reports will get some comments from the data editors on choosing better color maps if they're particularly egregious. Yes. And so it's nice to bring up some tools here that people can use to help with color blindness.
Oh, entirely. And especially in this day and age, there are so many tools that it's easy to. You don't have to search very hard to find something that you like. And if you don't like Adobe Color, or if you don't like Peloton, or there's many.
Right. Okay. That will bring us to
number 9. So number 9 on our list is assuming people know what you're plotting. So this is a huge challenge. I know I've run into this, and especially if you're going interfield. So this is something that I find particularly challenging when you're in a subfield of astronomy, especially where everyone has been working with this particular plot, and then somebody who's outside of the field just has no clue what it means, right? I remember the first time looking at some CMB plots and looking at power spectra of CMB, where you look at the left-hand side and you do not understand remotely what that variable is related to. It's like, an equation as the variable, where it's essentially some normalization of the power spectrum taken out. So a lot of this does go to speaking to what your audience is, but don't assume that people know what you're plotting based on that audience. The other aspect I see of this is somebody who's been working on their paper for such a long time will have generated these plots or been dealing with these plots for years, oftentimes. What's the longest you've spent on a plot, Frank? I've definitely spent years on a plot before.
Oh, oof. Well, for me, it can be largely an iterative process too, right? I will do a plot and I'll move it to the point where I think it's publishable. And then a year or so later, well, I didn't really do that as well as I could. And so then I will change the plot and then use that in talks and whatnot. So it can be an iterative process, but I have easily spent several months on trying to wire out a particular plot to make it appealing, intuitive, not speak only to the experts.
Mhm.
Yeah, I have spent months on plot design for
Sure.
some of my own publications.
And how do you deal with sort of plot blindness, right? Like, so what I'd like to talk about is sort of just the sense of you've seen this plot so many times that you sort of become blind to both, some of the things that are intuitive to you, but also sometimes some of the flaws.
Referee reports are great for this.
Referee reports are fantastic. That's right.
What is this all about?
Yeah. But definitely showing it to colleagues, I think, is a huge thing.
Yeah, it's a danger of restricting your audience to maybe 10 experts in the world who will understand the plot just by looking at it because they do the plot themselves.
Agreed.
So,
and also importantly, like there are a lot of standard plots that are highly hyper specific. A good example of this I know from Galaxy Evolution is the BPT diagram, right? That's something that a lot of people end up using. But even in that group, even in the people who know it, the way you actually plot it could be very different from, and the quantities that you're using to come up with that plot can be massively different. So having that very clearly labeled and indicated is super critical, right? And classic example, every astronomer goes through understanding a color magnitude diagram. How many different ways are there of plotting a color magnitude diagram? Yeah, exactly. You can keep counting, and there's probably somebody who will come up with another version, right? And so having that explicitly stated on the plot is critical.
Right, without necessarily having to read the caption or the.
That's right.
You really want your plot to be intuitive, grab like first it is, and that's the art.
That's fantastic. Let's go over to our number 8 tip. What is our number 8 thing to not do? Not rasterize your plots when you have large numbers of points. Okay, so this one's a little more technical, but who has gone to the archive? I know AAS, the journal-ready published versions tend to do a good job of this. And oftentimes, a shout out to many of the referees who have, commented on this, and so had authors fixed it. But if you go to especially an archive version of a paper and you open it up and suddenly you get to page 3 and it doesn't seem to load.
Right.
And you don't know why it's not loading until you wait 10 minutes. And then your screen just illuminates with literally millions of points in some cases. I've seen especially some Gaia papers where that's the case.
Yes.
I'm sure a lot of people run into this scenario. And one of the challenges is that you think, okay, so I'm plotting millions of plots or millions of points. It's going to take a lot of computer power to do. And the answer is no, it's not, right? Every computer, every modern computer in this day and age, if you have the ability to watch a YouTube video, it's got the horsepower to show a plot with millions of points on it. It's just the way that it's been encoded.
Correct.
And so one of the big challenges of this is knowing that, hey, this is so many points. There are easy ways of making that a raster graphic. So what the PDF or whatever you're outputting will want to do is it'll try to make every single dot a fixed point with its own properties, and then try to plot those specific discrete dots.
Right.
When what you can do in reality is much like a GIF or a JPEG image, you can actually just turn those into pixels, where suddenly it doesn't care about the very precise value you put in it. It cares enough to be able to actually just
like that pixel, right?
Exactly, that's right. Each of these pixels are a fixed address, and then suddenly it's super easy. So if you're using Python and specifically Matplotlib, and I know there are equivalents in R and other tools, but on any Matplotlib figure element or any, you can actually just add the rasterize equal true keyword. Just throw that in there. So if you do a scatter plot and you do a plt.scatter, just add in rasterize equal true, and it'll make just that element rasterized. So if you have 50 million points, rasterize equal true, it'll open up on your computer without a problem.
That's right. So I'll spill a little bit here since this is one of my pet peeves.
Sure.
So in general, I think you want to go, when possible, you want to go with a vector drawing.
Agreed. Yes.
Mathematical description of what the plot is.
That's right. Yes.
So the issue when you open up that PDF and it takes 10 minutes to render, for example, if you have 1,000,000 points, it has to figure out where those 1,000,000 points are, and it's a calculation. And in a lot of cases, the curve is fairly simple. So, you know, a simple curve like this, but when you actually look at how many, because a lot of times people will just dump it from a database or they'll dump it from a simulation,
right.
And there may be 10,000 points defining this curve. Well, you don't need 10,000 points to define that curve.
Yes, that's right. Yeah.
So one way around it is what you're suggesting here, which is just rasterize it if it's too much of a pain to do the other one. The other one is to learn how to control how many points you're actually plotting on a curve.
Sure.
It's like big business in cartography, right?
Right.
You learn how to decimate your data set so that the curve looks good, but it's only defined by 6, 7 points as opposed to 40,000 points. And this will also make your rasterized images or your vector images, illustrations render a lot faster by removing unnecessary anchor points.
Right.
Okay.
And that really speaks to sort of, you know, you do want things like, we love vector graphics. Vector graphics are fantastic. And they're the things that allow you to blow things up and still make them look perfect.
Right.
It's just that certain things were not meant to be vectorized in that exact way.
Right. Right. Very good. Yes.
All right, let's move on to our next point. Number 7 on the list. I wish we had a drum roll, but maybe we can put that in post. But let's move on to what is the making your plots a visual puzzle. So this is something that's really easy to do because oftentimes what you'll want to do in a plot is try to encode as much possible information in the plot. Right. You want, you know, every single visual element to be doing some work to tell you some information. Right. And the answer is that just makes it look much, much more complicated for somebody to understand the main story of your plot. So an example of this on the next piece is over here. So this is an example where you have 2 different elements being used to try to encode 2 different things. Right. And so for every point, I'm not seeing trends. Remember, one of the biggest advantages of making something visual and making something a plot is you can understand relationships. You can see how things are related to one another. That's not happening here because I can have to look at individual points and then look at both the color and the, you know, the object type to try to understand that. So I'm focusing on that one thing and not being able to see the relationship. And so this becomes a puzzle and I have to do a lot of work to try to understand what's going on here.
Indeed. Complete with legend and everything. Oh, this is just horrible.
Yeah. Oh, entirely. Absolutely entirely. It's incredibly difficult. And if you take a look at that, there is nothing to really glean. It's very, very difficult to understand.
A cloud of dots in the middle. That's what I see.
Exactly. That's right. That's
Which is not the message you probably want to impart.
Not at all. Yes.
Yeah.
And even if it was a cloud of dots and that was the message that you wanted to pass across, there are simpler ways of doing this.
Dot cloud. Right.
That's right. All right. Let's move on to our next, number 6. And that is using the wrong property of a plot for the wrong quantity. Okay. And so this is one that it's a little more esoteric, but it has, it has important implications. So if you think about the different ways that you can represent something on a graphic, on a plot as a whole, you can use the length of something. You can use the position, where exactly it is on the figure. You can use the shape of it. You can use the color of it. You can use the thickness of the lines. All of these are different properties of something that you visually see. But not all of them convey the exact same types of information. For instance, a good example of this is if you want to get a precise numerical value of something, the last thing you want to do is use color. Humans are not great at matching colors between a color bar and a plot to try to tell you what that exact number is. Right? That's not what it's useful for. What it's useful for is showing gradations or showing differences and patterns within the larger scale of that data. That's what color is very, very useful for. or in the case of not using color, black and white gradations. That's what it's good at. You're never going to be able to, read something to 3 significant digits off of a color bar, right? That's unless it's all black and that's the only value you have.
Right, or it's a distinct, 3 colors, right? And
exactly, that's right. Then, in fact, actually, that's a really good example of something to use color bars for, is actually categorizing something. That's a fantastic use of that kind of data. Color is fantastic for building categories that we can visually see very quickly. And so categorizing that data is great to do with color. However, if you want to do something that's super numerical, one of the ways to do that is using the length of something, or the location of it, right? If you imagine a scatter plot, the length or the location of each plot can be compared against its axes, and that can be used to encode precise numerical information.
Okay.
So thinking about what the property that you want to tell, is it, do you care that they know the precise value? Do you care about, just a larger scale from the min to max, how much it changes? That's what you should be using to think about whether or not you want to encode how you want to encode that information in the plot.
So I'll tell you one style, as long as we're on it, I'm currently infatuated with and experimenting for actual, publications. And they're not terribly popular in astronomy currently, but these are sparklines.
Okay, yeah.
So there are times when a sparkline is an incredibly concise way to get across the information you want to get and be quantitative about it without having axes, you'll often see it in sparklines in economic reports.
Yes, yeah, very much so.
Lines. But they can be quite effective in certain cases in astronomy. So I'm currently infatuated with experimenting with a new plot type of sparklines for astronomy.
Yeah, one of the things that I know there's a built-in LaTeX package for. I don't know if if we accept them in AAS journal styles, but you can actually do an inline sparkline in sort of a table or in text. I don't think we support that in the AAS journals yet, but
okay. Very good. But for example, what I'm particularly going to is not just one sparkline, but I will be doing a suite of calculations, varying parameters X, Y, Z.
Right.
You just stack up a whole number of sparklines, and then sort of at a glance, you can tell what matters and what doesn't, particularly at the end of the sparklines, you're putting some quantitative information.
Right.
How much the delta is or is not, plus or minus, that kind of thing. Yeah, they can be effective.
Yeah. And one of the things I think you're really leveraging there is that if you understand the one sparkline, just the first one, you've sort of understood them all, right? It becomes super easy to encode that data. And it uses something that often in visualization, the data viz community calls small multiples, right? It's that you're using a certain number of the exact same thing over and over again to tell that story.
Right. And it doesn't get much simpler than one.
Exactly. That's right.
It may go up and down in the middle, and that's okay. That's the point of it. But yeah, that's for those of you,
but incredibly powerful.
Check it out. It's an interesting way to plot things for certain hooks. Okay, number 5.
Number 5. What is number 5 on our list? It is
cluttering
your plot. So this is a huge one. It goes back to that same, notion that you want to try to put as much as you can. You want to fill it with information so that, it tells you everything you possibly would want to know about that data set or that plot. But what it ends up doing is it ends up making it harder for people to understand the basic idea of the plot and the basics of, what are you trying to tell? What is the story that's coming across here? So it's easy to think of, for instance, having, a big plot with an insert that tells you about one small part of that, which then maybe has another insert or another part is related. The simplest answer to this is if you're doing that much on a plot, probably need more than one plot.
Don't.
Exactly. Yeah.
Don't clutter your plot. I'll just make a comment.
Sure.
Over historical times. In the past, before everybody made their own plots, you would go to your local draftsman to make your figure. And least in my experience, sometimes a number of older papers, so things from the 60s, 70s, even 80s, when people were using Draftsman, a lot of those, some of those plots can be pretty complicated. There's a lot going on, but yet they're somehow clean. So there's just, I guess what I'm getting at is aesthetics of a plot change over time.
Right.
We're sort of moving into an era, it seems to me anyway, of simpler is better.
Sure. I think certainly that's true. But I also agree with you in the sense that some of these older plots were incredibly complex and can convey a lot of information without clutter. Right. And I think that that's the ultimate goal, is having something that has a lot of encoded information, but not necessarily having it look like a visual mess, essentially.
Right. Exactly.
Yeah. That's the sweet spot we're all aiming for.
Cool. And number 4, we're in the top 5. Number 4.
All right, we are in the bottom half of the list. All right, number 4, not annotating your plot. Okay, so this one's a huge one, and it's it's a common thing that I've seen. It's something I've done as well. One of the things that you want is, and I don't know why, I almost wonder if it's because we feel, especially as scientists, we want to reproduce something. So putting text on it at a specific location just seems like a lot of work, and it's not necessarily reproducible. But for that final version, you want to label it. You want to put things on it. You want to guide the reader and the viewer to what do they care about on this plot. And the easiest way to do that is to put a little text right where it is.
And of course, there's a little bit of there's design aspects on where you put that label, that plot, and how much you put on it. And it is a little time consuming because it's an iterative process, because you'll move the label, you look at it, and okay, over here, there. And whether you're doing it in a plotting program or you're doing it externally in let's say a vector editor, it takes time to do that, but it is so worth it at the end to have a cleanly annotated plot. It just conveys so much information.
And think about like how much of, just on a level of how much of that time that you spent in putting that plot together will go into selling your results and telling people about it and be shown in talks over and over again, right? A good, well-made plot will not just feature in the pages of a journal. It will go everywhere. Some of the most well-known plots are the ones that you see over and over and over again, every review paper, every, plenary session of a certain meeting. So a well-made plot really can get your results and data out there.
Has legs.
Yeah, exactly. All right, number 3. So this one is one of my personal pet peeves.
Okay.
It's when you are changing markers or colors for the same quantity in different plots in the same paper, in the same talk. So let's give you an example of this. Let's say that I have a perfect figure 1. That it has all of, it has colors that are chosen that are, sufficiently distinct. It has the labels associated at the right, at the right location. Great, done, figure 1. But then I move on to figure 2 in the same paper. And figure 2, in this case, figure 2 is in and of itself. If figure 2 was on its own, no one would care. But the fact that you have figure 1 there, where figure 2 is using different colors for the same properties or the same items, and also putting them in a different order. Right? These make it hard and require a person to think a little harder about how to compare these two. And it just makes it more difficult to understand the flow of the paper and the flow of the story you're trying to tell with your plots. So if we go to the next one, this is, what that would look like corrected. Now, if you see purple, you think quasars. If you see that kind of yellowish, goldish, brownish color, you think stars. And that's consistent throughout. One of the things that I often like suggesting to people is coming up with a set of, once you've experimented with your first couple plots for whatever the research project or the paper that you're associated with, write a little, I use Python often for my plotting, write a little file that just has those colors enumerated. So it's easy to just import and use them
Mhm.
over and over again. So you don't have to think about it. You can say, color underscore stars is this. And then if you need to change it, you can actually change it in the master file and it'll
Yeah,
reproduce all of those. And then it keeps it consistent.
right. Good tip. Good working tip.
So this is the obvious case where it's two things and they should be one-to-one. But one of the less obvious cases are as if we go to the next slide, where let's say that we're taking a look just at one of those categories, one of the items. So we're taking a look at some properties of the quasars. Right. It could be that we have luminosity on one side and mass of the black hole in the other side. Right. That's a reasonable plot that people who deal with quasars have made over and over again. One of the challenges, there's nothing inherently wrong with that scatter plot. However, one of the things to make it visually more tight with the rest of the plots and making that more consistent, so somebody looking at that plot can tell you what it is based on what else they've seen in the papers. If we go to the next slide, keeping that color in it.
Yes.
Right. So that ties it. And so you know that whenever you see something that's purple in this paper, it is a quasar.
Mm-hmm.
Whenever you see something red in this paper, it's referring to a galaxy, etc. And so this is just a nice, easy tie-in, a way of keeping the reader not having to think about the plot physically, but thinking about the result and what you're trying to present.
Yep. Uniformity of presentation.
It's so critical.
Yep, absolutely. Okay, very good.
All right, we're getting up. We're getting up there. We're at number 2, and the number 2 tip is, if you make your plots difficult to compare. Now, this is also sort of related to the previous one, but also a huge problem. So let's go. So let's say that you have 2 scatter plots. In this case, we're going to take that quasar plot, and we're going to take that galaxy, just take the galaxies on the other side. And here's the challenge. My eye will naturally want to compare these two. Right. And so I will just look at that without even thinking and be like, oh, okay, so the relationship looks the same. The points look very similar. They look like they're overlapping, but they're not. And the reason that they're not is if you look at the x-axis scale, you've gone from 1 to 100 versus 1 to 10.
Right.
And suddenly it becomes really hard, especially in log space, right? Like in linear space, you can do a little bit of translation, but in log space, it's really challenging to do that in your head. So especially if the quantities are directly related, and I know that this will increase white space oftentimes, but it's worth it to be able to compare, to have something that you can just directly put those two figures up right next to each other and say, hey, that makes sense with this, or this object, which is here on the figure, would be here on this other figure. So if we go to the next one, that's what that would look like. We've increased the white space, but now we can do a one-to-one comparison of the two.
And just to loop back on some of the other points we made, this extra created white space, don't look at it as white space, look at it as opportunity to put in some annotations to make it clear. So white space is not necessarily a bad thing. You can use it to your advantage.
Oh, entirely. In fact, especially when it comes to comparisons, white space is important space because it will tell you that something is not there, and that is often very critical to know.
Right. Absolutely. Very cool. Good.
All right. So before we get to our number 1 tip, our number 1 thing not to do on a plot, we've got some honorable mention things here to throw in there. So the first one, throwing out the code that made the plot. That is the worst thing that you can do. It's not actually about the plot itself, but I wanted to throw this in here because it is so important, because you will want to make that plot again. And more importantly, you will want to make other plots that look exactly like it to make those comparisons, to be able to do this. I'm still using some of the code and being able to compare some of the code from back when I was a graduate student to be able to reproduce things. And so keeping that code, super, super important. You will thank yourself in the future.
And sometimes you can even save yourself from yourself by, when you publish your article, to upload the data and processing to, for example, a Zenodo repository or something like that. And so one day when your computer crashes and your hard disk is wiped out and you go, oh, what was that code for that plot? Zenodo will be there to save you.
Which, for the record, is not is a matter of time. Your computer will crash at some point. You will lose your hard drive at some point. It's not a matter of if, it's when, and this will help you.
Absolutely.
All right, number 2, making your caption too brief, right? You can, I'm sure many people I know, I was taught back in high school of like when you write a figure, caption of a scientific figure, it should say what the X quantity is and what the Y quantity is, and that is your caption. And that is not cutting it anymore. Especially in this day and age where there are literally hundreds of papers that you could potentially read that is directly related to you in any given week. People read through plots. People will try to understand the results primarily through the graphical and visual elements of this. And so the caption should reflect that. The caption should encapsulate not only what are they looking at, but what is the message that they're trying to convey within here.
Very good. Indeed.
Let's go to the next. So using too many fonts. This is
pet peeves.
it's a big pet peeve of mine. Choose your font, especially in this modern age of the variety of different plotting softwares. You can choose whatever font you like. I personally have my own preferences, and I have a distinct hatred for Computer Modern. That is something that I just really, really aggravates me when I see it. But one of the things that's most jarring is if you see, and it's one of those things that's also you don't realize that you find it jarring, but that's harder for you to understand something, is if you see a bunch of different fonts on it, on a figure that's annotating it, you'll often try to associate those different fonts with different properties or different, they're not necessarily associated with one another. And it takes just that much longer for the person who's looking at the plot or looking at the graphic to understand what's actually going on and that they're all really meant to do the same thing.
And I should add here that too many fonts, it not only refers to the font family, but also to the styles within that font family. So if you're using, for example, regular, italic, slanted, boldface,
small caps, for instance.
Small caps like that. Yeah. So it not only just too many fonts, but too many styles within that font also applies here.
Something I would recommend strongly is actually thinking about a hierarchy. What are the, what's the main title kind of style that you want? What's the main highlight kind of style? And what's the base style? With those three, you should be golden.
Yep, absolutely.
And I think the last honorable mention is using a plot when a table would be better. So I am a big fan of visualization as a whole and of plotting as a whole. I think it's super important. I think this is the part of the reason why science is as a whole and astronomy is where it is today, is because of the use of visual information to better understand the science. But there are times when we take it too far. There are certainly times when what you're trying to convey with 4 numbers really should just be 4 numbers in a table. Right there, you've added 0 by making it a 3-dimensional plot with like each of the bars being like the shape of a galaxy or something like that. Right, that is not helping anyone.
Right. Yes. Tables can be useful, particularly if you're looking to get results that other people will use in their models or on their observations. So that's providing the direct quantitative information that they can use. That's often more useful in crazy plot.
Yeah, and there's a lot of things that you can do in a table to actually make it visually comparable as well. So right off the bat, one of the things that is often talked about in statistics courses is things like STEM charts, which are just tables, right? They are just tables that have specific orderings of what the values are. And so doing things like, for instance, bolding or changing, what the top value is in a given table really helps that make it much more visual.
Yeah. All right. And we finally come to
number 1. All right. Number 1 thing to not do in a plot is to hide the lead. And what do I mean by this? At the end of the day, when we're talking about a paper, we're trying to tell some story of a scientific result. We're trying to tell people something about how the universe is working or how the instrument that you built is working. And one of the easy things to do, especially when you started looking at the data for the first time, before you've come up with that conclusion and you know where the story is headed, is you'll try to make the most basic plot where everything is fair and comparable, right? Like scatter plot, you have two quantities, you'll try to scatter plot it to see what's going on. That's great, and that's critical, and that's important, but that should not be the plot that appears in your paper, right? At the end of the day, there is usually some story that plot is trying to tell you.
Right.
You will want to annotate that. You will want to highlight it. You'll want to give the appropriate context, right? One of the easiest things, or one of the most challenging things I found, is that people will produce a plot where they'll show like these are where the data points lie, and that's why this is interesting. But you'll have to compare back to the first or the second figure to try to understand the context of it, and so that makes it harder to understand why it's an interesting plot. So think about one of the easiest ways to deal with this challenge is think about what is this plot trying to tell me, and is it obvious that it's telling me this, right? This is not a point for a mystery or a game of hide and seek. You want that to be obvious.
Yes. Yes, the money shot.
Right. Yep, that's right. That's right. But that is the top 10 things, with a couple extra thrown in, of things to not do on a plot.
Very
Frank,
good.
do you have other, what was your worst pet peeve of the plots that you've seen? I'm curious.
Oh, my personal one?
Yeah, your personal one. The one that you've seen a plot and you're like, no, this cannot stand.
Well, my number one is people who insist upon rendering 1 million anchor points in a vector plot. I mean, we covered that. That one particularly grates on me. For various reasons, but that's the one. So that's the one. I've seen all these sins in papers that have been submitted, and I'm not immune. I have certainly done some of these myself over time.
As have I. Yeah.
It is a learning process, right? Nobody's born knowing how to do this, so you can learn. So mistakes made in the impetuousness of youth can be corrected.
Yes, that's right.
In subsequent plots. So yeah. So actually, I found this discussion very useful, because it's just a reminder for maybe experts who've made a bazillion plots, on just reminders, and for newcomers, it's pitfalls to watch out for, and for those in the middle, it's like, oh yeah, I really should be doing this. Not doing this, as the case may be. So yeah, I really enjoyed it. So thank you very much.
No, thank you so much for having me. And this is going to be. Yeah, this is going to be a lot of fun as we continue to dive into a lot of new data topics and coding topics, and helping everyone and helping all astronomers across that are watching this YouTube channel really be able to deal with their data better. I think that's one of the exciting things that we're hoping to come out of this.
Yeah, so we're kicking this series off. So this is number one. I believe that we've sketched out roughly 10.
That's right.
Forward in the future. So if you want to say anything about those, or drop a juicy lead on the next one or something like that, go for it.
Yeah. So a couple. The ordering is going to, let's. I'm not going to make any promises about the ordering, just to make sure that that we keep our word. But some of the things that we're hoping to take a look at is looking at, for instance, tools that astronomers should be using from outside of the astronomy community. So we all kind of know about often the things that are in astronomy, but what are other people who deal with data using, and how can astronomers use them better? That's one that I'm really excited about, because I think it will add a lot of power to our already incredible tool set that we have. So that's one I'm excited about.
Yeah, and I gave one example earlier today on spark lines, right? Not super common in astronomy, but can be very useful. So that would be very nice. Okay, I think that'll do. So Mdi, Thank you very much. And we will certainly see you on the next one as we kick off this new series. Oh, and if you have ideas for topics that you would like to have covered, or things that you didn't like that were covered, neither one of us are very hard to get a hold of.
That's right.
Web presence stuff in the description below the video. And we'll probably put a link if you would like to have the PDF of what we talked about. We'll be putting that probably on Zenodo or maybe GitHub. And we'll put a link to that in the description below the video as well. So that'll do. Thank you very much, everyone. And we'll see you on the next one on this data series.
Until next time.
Bye-bye.